All right, question right off the bat here. Right off the bat, we are talking about this week we're developing ideas of current, right? And got a question for you. Speed of the electrons in a typical current carrying wire is what? What do you think? Be fast. A. Well, you're right. No, it is A. Congratulations. You got one right. All right, good. It's A. It's painfully slow. It is really slow. Electrons do not move fast. That's a very common misconception about electricity. That's based. Get the boy, you better get out of here.
Junior.
My goodness. Behind the green screen, my son's like, hey. I'm like, okay. That's a very common misconception about electricity. That's basically what we're talking about here. It is slow. It is very slow. However, when I hit my light, comes right on, right? Comes right on. This is, and I think I might have mentioned this last class or something, or one of the classes, but the analogy is, when I turn on my faucet for like the water immediately comes out, right? Even though there is, even though ultimately it comes from, I don't know where it comes from. I just get the water in my house. I pay a bill and I'm not even sure it comes from some place where they have a lot more water, and but I don't need the water to come from the plant directly to my faucet, right? There's water already sitting in the pipes. And for electricity, it's the same deal, right? The electrons are already sitting in the wires. And I'm going to do a derivation later where we can sort of see how this stuff works. So, if I were to hypothetically on the next exam give you a question just like this, you'd get it right. You would say A, or the option that's like A. Okay, now that I said that, I'm not obviously going to put that on the exam. But maybe I will. It's all about the mind games. All right. So, we are going to start looking at the concept here of how electrons flow, what we call current. In this particular example here, we have our charged capacitor. Say they're separated. And there's an electric field that's present between them, and a voltage, right, gets established between the plates. When we connect wires, okay, a wire, some kind of conductor, really, to the capacitors, we start to see a discharge. The discharge is a flow of charge in the wire that will eventually allow the capacitor to be neutralized. So when we talk about a current, we're talking about a flow of charge in the conductor. You got to remember something about this stuff. I don't think I'm recording. Am I recording?
No, you're not.
I'm recording. It's just I don't remember pushing the button. So I was freaking out for a moment there. All right, I'm try to calm down and let's get back to this. So that flow of charge in there is what we mean by the concept of current. So what we're going to try to do is we're going to try to characterize how exactly that occurs. And I was in the middle of a point. What was my point? I said something about, I don't know. What was I saying? Saying something. Wires. Oh, no. Something. I had 2 points. I'm mixing them up. I don't know. I'll just keep going. All right. There are some physical signs of the current in a wire. Oh, that was my point. It's at the top. It's at the top here. This is my point. We're not dealing with electrostatic equilibrium anymore. So some things now don't apply because, like, for example, there's no electric field inside of a conductor, right? Kind of. If you have an electrostatic situation, that's true. If you have a potential difference established, like a constant potential difference, like say you're hooked up to a battery, well, that's not true now because we're not dealing with an electrostatic phenomenon. We're dealing with an electrodynamic phenomenon. And so a lot of those rules are going to change. So that was my point. I'm glad I remembered. I didn't remember it actually. My notes here. That's why I have them for me, not for you. All right. Now, like I said, the wire can heat up. That is a sign of that. There is a magnetic field that is generated actually as a result of current. We can see that when compass needles deflect. In fact, that was one of the important discoveries made about current flow, is that it was noticed that there was magnetic phenomenon associated with current flow, which is interesting. Okay, so the electrons we know are the charge carriers, right? They are much lower mass than atomic nuclei, and they're the ones that are going to be free to move. We've talked about this concept before. It is the sea of electrons. Okay. And so we got to be thinking about how electrons can flow through material when there's all these big giant atomic nuclei in the way. Okay. So this is going to be tricky actually to think about. But we'll do it. So we are going to define a quantity called the electron current. Now let me warn you about this quantity. This is a modern idea of current. And unfortunately, this is not how we're really going to be thinking about current after this week. And the reason why is because a lot of the conventions for how current works is based on ideas that were developed before we knew electrons existed. But to really properly understand how current happens, we're going to take the more modern approach first to introduce the concepts, and then we're going to switch over to that more archaic idea. That's just the way things work, unfortunately. All right, so the electron current, and we're going to take, and we don't have to take a circular wire for this, by the way. I'm just going to do that because it's very common, and the actual shape of the wire ultimately doesn't really matter, okay? But the electrons are going to, when in the presence of some kind of potential difference. So, it's not an electrostatic problem. There's a potential difference that is established in the wire, and the electrons move according to the electric field. But the electron current is going to be a number of electrons that pass through a cross-section of the wire per second. And so we're going to start off with this little relationship down here. This electron current is number of electrons per second times a given interval of time will be the number of electrons that have moved through that cross-section. So both of these numbers here, quantities, the capital N sub E, the lowercase I sub e, are in terms of a cross-section. Okay, we start there. Now, if I consider a cylindrical piece of wire, okay, because again, the math is easy and it could be really any shape at all, the number of electrons can be specified in terms of a electron number density. I'll say more about electron number density in a moment here, times a volume. So this is just your traditional idea of density. Number per volume, okay, that's density. The volume here, though, can be broken up a little more finely. We can talk about the volume of the cylinders being the cross-sectional area times a delta x, a distance moved in x. Then the delta x, the drift velocity is effectively constant. And again, I will provide you that justification a little bit later in the lecture today, but effectively constant. And so you can specify the drift velocity as being a change in x over a change in time. So replace the delta x here with drift velocity times v. So if we compare this relationship to the thing we developed before, n sub e a vd is the electron current. So as you can see here, it depends on three factors. The number density of electrons, which is a material-dependent quantity. You just need to look, it's in tables. It's not something you ever figure out. It's something that you have to look up. It's like coefficients of friction. Okay, you got to find the values for your substance. A is the geometry of the conductor here. So if this is cylindrical, as we're talking about here, it's the cross-sectional area of the wire. And VD is the drift velocity, which we'll have to develop the drift velocity a little bit later, because honestly, what's the ultimate reason why electrons are moving? It's because there is an electric field in the wire. And so obviously the electric field's not involved in N sub B or A, it's involved in D. So we will develop that idea in a minute, but let's explore this a little bit more first. All right, I gotta erase my lines here. Clear, yes. A wire carries a current. If both the wire diameter and the electron drift speed are doubled, the electron current increases by a factor of what? What do you think the answer is? The answer is, I saw a letter. I saw a letter. Where's this letter? I missed it. Daniela. D is correct. Because the cross-sectional area goes as diameter squared. The electron drift speed is linear. So you have a 2 squared factor and a 2 factor, and you get a factor of 8 overall. Okay, excellent. It's D. It's D. Okay, now, these are numbers taken out of not your textbook. This is an old textbook I used to use way back in the day. But the values don't really vary by much. In fact, I would be shocked if these values varied really at all from your textbook. So just use these values here or use ones in your textbook. Don't attempt to look these up online because you tend to get a million different numbers and I don't even know what the hell most of them even mean. So this is the numbers that you want to use here. This is in units of electrons per volume, which would be meters cubed, right? So, and this is just basically the amount of electrons available, right, in the substance to produce the current. So what will happen in problems is you'll be told a substance. They'll say a copper wire, and you'll need to know that if electron density is needed, you'll have to put in this number here. So it's one of those things you'll need to be mindful of when you read the problem. If they mention a substance, then you're going to want to look up the value for it. Okay. I think I have some problems here. I do. Excellent. All right, let's do these. Bring up my slides here. We have 1 times 10 to the 20 electrons that flows through a cross section of 2 millimeter diameter wire in 5 seconds. All right. So this is a big mess right here, right? We don't want diameters. So we have a 1 millimeter radius wire. That's pretty much your standard 12 gauge right there. Although I don't need no, it's not. Nobody uses iron. You could, oh. You could. I bet it heats up too much though. That's the problem. All right. So I'm going to use. I want to know what the electron drift speed is. So the equation we have right now is the electron current equals N sub E A V D. However, I want to know the electron drift speed, so I'll need to know these three quantities. I don't really have electron current, but I kind of do because it's simply going to be the number of electrons over the period of time. So when I solve for VD, I get the relationship that is right over here. So now this is all the numbers that I need. So I plug in the number of electrons, and you just simply plug in the number of electrons here, okay? Now, some things we want to be mindful of here is that at times they'll tell you the amount of charge, okay? That, and, for an excess amount of electrons or something like that, and you have to convert that to numbers. So right now, there is no mention of charge right now. Just to be clear about that, we have not brought up charge. So the period of time is 5 seconds. The number density, the electron density for iron, we got to look up in the table there. Let me just double check that number because I don't remember that being right. It's the same as copper. Okay, fantastic. Let's go back. 8.5 times 10 to the 28, and then we're going to divide this by a cross-sectional area. Make sure you do meters, and make sure you do the radius, unless you want to use your diameter formula. But nobody uses the diameter formula for area. Don't be a weirdo, all right? Use pi radius squared. And we end up with a very small drift speed here, 7.5 times 10 to the minus 5 meters per second, right? So that's, what is that? That's not even, that's like a millimeter per, minute or something? It's very small. All right. Question number 2 here is we have electrons that flow through a 1.6 millimeter diameter aluminum wire. Okay, the radius is 8 times 10 to the minus 4 meters. We have the drift speed. How many electrons move through a cross-sectional wire each day? So I'm going to use the same equation, using the electron density equation, but I'm going to put that in terms of number of electrons over time. Very similar equation we had before, but we're going to solve for the delta T here. No, we're not. Oh, we want how many electrons? So we're going to solve for the capital N sub E. So this is what? Aluminum. You got to get the value for aluminum. It's 6.0 times 10 to the 28. Cross-sectional area, pi, 8 times 10 to the minus 4 squared. Your drift velocity is 2 times 10 to the minus 4. And the amount of time, and the time that I'm going to put in here is going to be how many seconds are in a day. We're going to stick with the standard SI day. Don't be a smarty pants and put in the sidereal day here. Just put in the normal day, 86,400 seconds. Put it all through. What do we get? 1.0 times 10 to the 24 electrons. Not very many. Not very many, actually. All right. Straightforward stuff, but what's going to happen, and one thing that's a little tricky about this stuff is there's a lot of equations. They're going to be developing lots of little equations, and so you got to have to balance all that stuff. You got to have to figure out what to be used when, and you'll see the examples. That's how we'll work this way through. Okay. So let's talk about how this is actually going to occur. How long should it take to discharge this capacitor? This capacitor is charged to 16 nanocoulombs. That equates to having 10 to the 11 electrons on the negative plate in an absence from the positive plate. When we connect things, the electron current is going to go from the negative plate towards the positive plate. Typical drift speed, 10 to the minus 4. Okay. So if you have a 20 centimeter wire, for example. Not too long, right? Not too long. What is that, like 8 feet? I mean, not 8 feet, like 8 inches, right? Doing that number in my head right? I don't know. Something like that. The electron would take 2,000 seconds, right, to go through this wire here. It doesn't do that. It doesn't do that. Because at this speed, if the electrons are really just going to travel from here over to here, it would take an extremely long time for that to happen. At this kind of drift speeds, it's not going to happen anytime soon. A real capacitor will discharge instantaneously. What that tells us is that these electrons that are built up over here are not going to end up on the right here. In fact, all the electrons that are built up here will actually stay in here. That's true. They will stay here. Let me explain that. All right. There is electrons on the negative plate, right? There's some excess electrons, but then the whole thing has electrons. Okay, so we were just talking about excess electrons. And then the entire wire has electrons. So we could work this out here. Say we 10 to the 11 electrons, right? Now, the number density of electrons for copper is 8.5 times 10 to the 28. Okay? You take that number there, and we're going to divide that. You can take that number and you can divide by, let's do it here, let me think. So I'm going to take that number, 8.5 times 10 to the 28. That's the number density for this stuff. And then what I'm going to do is I'm going to multiply that. I'm going to divide that. Actually, hold on, let me think here. Because here's what I'm doing. If I do... So if I do the number density of... You kidding me? Come on. Don't do this to me. Number density of electrons is going to be the number of electrons divided by a volume. And if we take this to be a cylindrical thing, pi radius squared times some delta x. I'm just trying to figure out how many electrons are in a little segment delta x. So I'm going to solve for delta x here. So it's number of electrons, it's 10 to the 11. No, it's not 10 to the 11, come on. Okay, I'm going to divide that by the number density of electrons, 8.5 times 10 to the 28. I'm going to divide that by pi. And then the wire, a 2 millimeter diameter wire, 0.001 squared. That's a standard household wire, right? I think that's basically 12 gauge, which is, it's what you find in houses. What do I get? 3.7 times 10 to the 13th. Now, whatever figure I got this from, they came up with 4 times 10 to the minus 13th, but still minus 13th. That distance is small, people. That distance is small. That is less than 1% the diameter of a copper atom. Less than 1% the diameter of a copper atom. What happens is, in that wire, all the electrons shift slightly. How slightly? 0.7 pico, no, 0.4. Oh, I got the same numbers they did, actually. Never mind. I got 3.7 times 10 to the minus 13. So 4 times 10 to the minus 13. That's 0.4 picometers, right? I mean, like a copper is like 100 picometers or so. I think that's how large a copper atom is. Maybe a little larger than that. So the entire shift in the electrons is very, very small. Incredibly small, actually. Okay. So, and then the question is, at the drift speed, 10 to the minus 4, say it's 10 to the minus 4, and the electrons have to move, tenths of a picometer. What does that come out to? It comes out to basically nanometers. Nanometers is what it comes out to be. So, I mean, if I do this number divided by just a regular 10 to the minus 4, That's kind of fast too. 4 nanometers. 4 nanometers. Fast. All right. So now what we're going to try to do here is we're going to try to connect the electric field now to what's going on with these electrons, this drift speed. Right? Now you got to remember what's going on here is this. Electrons in that wire, while they are experiencing an electric field, and at moments in time, if they're accelerating, ultimately the motion of these things is as if it's a constant speed. In fact, one analogy you can give for this is it's like pushing a book across a surface at a constant speed. The push that you give is like the electric field. The friction that pushes back is basically the forces that are exerted on the electrons as they collide with the nuclei of the atoms. It's not empty space inside the conductor, right? The electrons, if they're going to flow through, they have to be able to, navigate around all these gigantic atomic nuclei, which is not easy to do. And so the combination of these forces results in what effectively is a constant speed as it tries to move through the wire. Okay. Now, this example here is right before we want to connect up the capacitors here with the wire. At the moment, right, this is a electrostatic situation. The electrons will distribute themselves over the entire surface of the conductor, which involves the capacitor plate and the wire that's connected to it. As soon as you connect the wires, then you are connecting two regions that have a potential difference that will generate an electric field, and then the charges start to flow. And what will initially happen is you'll get a non-uniform distribution of charge as things start to move. Okay, and what we find is that non-uniform distribution of charge establishes an electric field inside of the wire. Okay. There was one more thing about this. Here they're showing the direction of the electric field, which is the flow of positive charge, which is, again, this is that old archaic way of thinking about things. But initially there's this buildup as charge moves through, and that unevenness creates this electric field. And I think we're going to develop that next class. We're not going to get there today, I believe. Oh, no, we are getting to there today. Ooh, never mind. All right, so here, now we've done this problem before, actually. We've done this problem before. What is the electric field on axis due to a ring of charge? Right? We developed this a while back en route to determining what the electric field is due to a conductor. Now, we're not going to go back and dig up that old equation, which was kind of wild. Here we just need to realize that the electric field on axis has a particular value to it. And because you have this uneven distribution of charge here, you have a lot of competing electric fields. For example, down on the more positive side, we'd have rings of charge that are going to be larger in terms of their amount of charge than ones that are closer to the more negative side of things. And they both have electric fields that are associated with them, except the electric field due to the greater charge is going to be greater. So there will be some canceling out, but not completely. And so we have a net electric field that points toward the more negative side of things. And as we move through the wire, that distribution slowly changes in such a way that we maintain the electric field on the inside. So remember, before everything's hooked up, all the charges exist, right, on the surface, okay? those surface charges generate an electric field on the inside, and then charges flow on the inside. Okay, and that is ultimately what's going on with any kind of current carrying wire. Is the potential difference allows this non-uniform distribution of charge, which establishes a magnetic field, electric field, not a magnetic field. Okay, so question for you here: surface charges distributed on the wire are shown. The electrons in the wire are going where? Okay, so electrons are going to float towards more positive charge. They move to the left towards more positive charge. The arrows in here, sorry, I merely saw the arrows and I thought I was talking about the electron movement. This is the electric field direction to the right. So the electrons are going to move to the left. Okay. All right. So here is what your typical electrostatic conductor looks like. It has this sea of electrons. And the electrons are going to have random motion due to thermal energy. And they're basically going to be bouncing around all the atomic nuclei that are here. Now, overall, though, if you were to work out, they have some given speed. It's given by the Boltzmann distribution. That's a whole other subject. And then when they collide, they rebound off. We can assume that's some kind of elastic collision. But ultimately, what's going to happen here is if we work out the distance traveled over time, the overall displacement is going to be zero here. Okay, there's nothing that's going to cause a bulk motion spontaneously. You can also argue that's a thermodynamic argument as well. But we flip on the electric field, and now we have this setup. We have the electron is experiencing an acceleration. And so it travels for a distance, and then it hits one of the atoms. Then it bounces off, but then it's still under that acceleration, so it drifts a little while. Then it hits another one, bounces off, hits another one, bounces off. So there's tons of these little collisions that are taking place. And in some cases, those collisions can actually cause the electron to travel the other direction for a little bit. But because you ultimately have a field here, these things will experience a net displacement. All right, so let's explore. Don't blow up, please. Don't blow up. Please. I'm going to teach another class later today. All right. So here is a graph that demonstrates what the velocity versus time graph might look like. Now, this is a strange graph. It's like a sawtooth graph, right? And so what's happening here is there's a slope to the velocity graph, right? You know what slopes on velocity graphs mean? It means there is an acceleration. So what's happening here is these electrons are experiencing an electric force, E times the electric field. And, in between collisions, that would be the only force that they're experiencing. So this would be the mass of the electron times an acceleration. All right. But here's what's happening here. The electron moves a certain distance, and then it hits something, right? It hits one of the ions, and then it gets its velocity instantaneously changed to the collision. Then it continues. So at this first collision right here, it actually changed direction. And then it started to slow down, turned around, and then it started moving back, right? Then it hit something again, did the same thing, turned around, started to slow down, changed direction, got hit again. All these dashed lines are when things get hit. So while there's an acceleration taking place, fine. But as I mentioned before, the ultimate result of all this stuff is that you really don't have an acceleration, that you have a constant drift speed. And so what we're going to do is we're going to state this acceleration a little differently. We're going to state this as the drift velocity times, divided by, not times, times an interval of time. And the interval of time is what we call the mean time between collisions. And that is given by this Greek letter tau, mean time between collisions. So this delta t here is what that is. And if I solve for the drift velocity in this relationship up here, I get this thing down here. And this is a really nice quantity. Very nice. Very, very nice. I'm very happy for this thing. Here's why. We had a concept of electron current that was dependent on some material things and drift velocity. But we know there's something deeper going on in the drift velocity, right? Well, this is what's deeper. Ultimately, we've tied this to the electric field. And so the drift velocity is a function of a bunch of material-dependent quantities. The charge of the electron. The mean time between collisions. Again, that's a material-dependent quantity. The mass of the electron. That M down there has got a little e. Mass of the electron. And that whole thing is times the electric field. So we have a one-to-one correlation between drift velocity and electric field. That's very satisfying that we can do that. We have one more thing to do with this, though, which we won't do today. And what we're going to do on Wednesday is we ultimately need to tie that electric field to a potential difference. Because that's the practical stuff. That's what we spent all the time working on. And so we're very close to that point. Okay. So, putting it all together, we take my equation for drift velocity that we developed in the last slide, plug that into the electron current that we have here, and we end up with this relationship between electron current and electric field. So the electron current is a function of a lot of material-dependent quantities. Everything in the fraction there is a material-dependent quantity. Only the electric field is something that's independent of the materials for the most. All right, so we need to work out for the first one here the mean time between collisions. Oh no, we got that. What do we want? What do we want here? We want something. We want an electron current. What do we got? We got mean time between collisions. We got tau. We got iron. So we know N sub E. What else do we need? We already know we need the area though. There we go, 1.8 millimeter diameter. Well, I think we got everything we need. Let's plug all these numbers in. All right, so we need the iron's value for the electron current. Electron density, sorry. We have this charge of the electron. Mean time between collisions. Look at this, 4.2 times 10 to the minus 15. You know how fast that is? Crazy fast. Crazy fast. What's that? It's called femtosecond. I don't know. I'm not going to think of it right now. Okay. I'm not going to think about it. Not going to think about it. All right. So we put all these numbers in. Don't forget, we are dealing with, we need to put the wire's dimensions in meters. And we're doing our pi r squared. Okay, don't be a weirdo. We get 1 times 10 to the 19 for our electron current. So every second, 1 times 10 to the 19 electrons pass through the cross-section of the wire. All right, not bad, not bad. I don't know, this time is bugging me. This time's bugging me. It seems too quick. Too quick. I'll think about it later. All right. We have an electric field. It creates an electron current of 3.5 times 10 to the 17. What's that little? Oh, that's I sub B. Again with the diameter. Again with the diameter. Again with the millimeters. We got aluminum this time. What is the drift speed? Okay, so what I'm going to do here is we have a real simple equation for drift speed. Right? This is the equation we developed at the beginning. So I have my electron current. I have my number of electrons per volume because it's aluminum, which I believe is 6 times 10 to the 28. It is. Got to make sure you put your radius here. 5 times 10 to the minus 4. All those numbers go in there, and we get a drift speed of a pathetically slow 4.7 times 10 to the minus 6. All right, so aluminum wires, I don't know about that, right? We want to know what the mean time to collisions is, and so I'm going to opt to use the equation that we developed for the drift velocity here, because I have everything here. I need to find tau, and I have the electric field, right? So I'll solve for that. Make sure you put the electrons information in here. Put my drift speed from part A, all right? But don't forget, don't put a rounded number in there. I got 4.7, but that's not what I actually got. Whatever the calculator says, you put that number in there, and I got 2.1 times 10 to the minus 14. All right. So this stuff is not exactly challenging, I'll be honest, right? Not exactly challenging. I'm being honest with you, right? Not exactly challenging, but there's a lot of equations. There's really sort of 3 major equations that you want to keep in mind. Right? 3 major equations. There's some redundancy. There's this one here. There's the drift velocity equation, and then there's another equation for electron current. Ultimately, there's really 2 equations, but when you do your homework, you're just juggling these equations here, right? And the purpose for this stuff is to develop the idea of current. Wednesday, we're going to start to look at our materials and start to look at the potential difference across. And then we have to start exploring, really what it means for substances to have. Because right now we have a lot of material-dependent quantities, right? We got electron density. We got this cross-sectional area business. We got drift, we got mean time between collisions. And another factor that we're going to talk about next time is the length of the wire. That matters too, eventually, right? And that's a little obnoxious, having 4 different material-dependent quantities. And so what we're going to develop on Wednesday is one quantity that takes all of those things into account. And that is what we call the conductivity or resistivity of material. And that will directly relate to the electron current. And then from there, we can develop the idea of standard current, which is the flow of positive charge. And at the very end of the lecture, we got Ohm's law. And then we can dig into circuits. All right, I'm done.